Our new topic is pressure of solids. The definition of pressure is, it is defined as the force per unit area. When we take the mathematical model of pressure, P is equal to F over A, the force per unit area, where here P is pressure, F is the force, it is in Newton, A is the area, it is in meter square, so the unit of pressure from here will be Newton per meter square. What is important here is the force generating pressure should be perpendicular to the surface. Here, as picture, you see that the force is perpendicular to the surface. So here the pressure created by the force is equal to F over S. But in this example, the force is not perpendicular. It has an angle of alpha with the vertical line. So I'm going to here divide the pressure, the force, into components. Now, when I apply this force, that means that I have one parallel to the surface and one perpendicular to the surface. So this component has no pressure on the surface because it's not in contact with the surface. But this is perpendicular to the surface. So here the pressure will be the vertical component of the force over S. As here the vertical component is smaller than the force, then let's say this P2, this P1, I can say that P2 is smaller than P1. So I can conclude here that the more perpendicular the force is, the more pressure it exerts. Let's solve an example. For an object sitting on a surface, the force pressing on the surface is the weight of the object. But in different orientations, it might have a different area in contact with the surface and therefore exert a different pressure. Now I have the same two objects with a weight of 100 Newton. Let's say the pressure at the base of the object here is P1 and in the second configuration P2. Now P1 is equal to, from force over area, the force here is the weight of the object, which is equal to 100 Newton over the area 0.1 meter square, so which is equal to 1000 Newton per meter square. But in the second configuration, again from the formula, the force over area, the force is again 100 Newton, the weight of the object, but this time the area is smaller, 0.01 meter square, so the pressure will be equal to 10,000 Newton per meter square. So the same object with different configurations have different pressures. So as the area gets smaller, the pressure gets bigger. Let's talk about some units. We said that the unit of pressure is equal to Newton per meter square, which is equal to Pascal. So 1 Newton per meter square is equal to 1 Pascal. This is the symbol for Pascal, okay? You can use Pascal instead of Newton per meter square. There are many physical situations where pressure is the most important variable. In the first example, in peeling an apple, you want your knife to be sharp, so you keep the area minimum in order to get a larger pressure. Getting an injection, again, minimum area and larger pressure, so easy to inject, less hurt. Or cutting a wood with an axe, again here you see that this area is minimum in order to increase the pressure. If you divide the object vertically as in the figure, the pressure of each part will be the same as the original one. Let's say this object has a weight of 3G with a base area of 3A. I divide here into G and 2G parts. Let's say this has a pressure P1 and this has a pressure P2, and P1 is equal to G over the area A. P2 is equal to 2G over the base area 2A. So you see that I again get the ratio G over A. The total one will be equal to the total weight over the total base area, again, which is equal to G over A. So if you divide the object vertically with symmetry, then the pressure will be kept constant. This property of pressure in solids is very important. Solids transmit force only in one direction, in the direction of application, without changing its magnitude. Now here I see a nail and a hammer. I apply a force F1. This force is transmitted by the nail to the edge of the nail. So the force F2 is equal to the applied force F1. Now, you know that the head of the nail is greater than the edge of the nail. I mean, A1 is bigger than A2. So the pressure, let's say, created at the head of the nail is P1 and at the tip of the nail is P2. P1 is equal to F1 over A1 and P2 is equal to F2 over A2. So as the forces are the same and A1 is bigger than A2, so I can say that here the pressure P2 is bigger than the pressure P1. So here I created a bigger pressure with the same force applied. In this example, compare the pressures of the given blocks with same mass. Now here I have an area of A1, this has an area of A2, and this has an area of A3. They have the same mass, so the same weight. So the weight of the objects is equal to the force, so they have the same force. Pressure is equal to a proportion to the force applied. This is the same in three figure over the area. Pressure is inversely proportional to the area. So here I see that A1 is bigger than A3 is bigger than A2. As pressure is inversely proportional to the area, so P1 is smaller than P3 is smaller than P2. Another example, find the ratio of the pressure applied by the objects in the figure with given densities, base areas, and heights. Now the densities and the heights are given, so I'm going to find the weight of the objects. Let's say this is the object 1 and this is the object 2. The weight of the object is equal to mass times gravitational acceleration. Mass is equal to density times volume of the object. And volume is equal to base area times height of the object. So the weight of the first one is equal to 80 AHG, and the weight of the second figure is equal to D times 4A 4H times G. So you see here that this is twice the weight of the first one. So I can say, let's say G, this will be equal to 2G. So pressure at the base of the first figure is P1, which is equal to weight of the object over the base area. The pressure at the base is P2. This has a weight of G, and this will be transmitted by the second figure. The second object has a weight of 2G, so the total force exerted on the base will be 3G over the base area 4A. So the ratio of the pressures will be equal to 4/3. Compare the pressure of the given identical objects. As they're identical, they have the same weights. This has a weight of, let's say, G, and this has also a weight of G. Here you see that the weight is perpendicular to the surface, but this is not perpendicular. So I have to take the perpendicular component, but the perpendicular component will be smaller than G. So as force gets smaller, then the pressure will also get smaller, because pressure is directly proportional with the force. A, they have the same base area, no change. So as F gets smaller, P gets smaller. So let's say the pressure at the first figure is P1 and the pressure at the second is P2. As force gets smaller, then P2 will get smaller than P1. So we can say that the more perpendicular the force is, the more pressure it applies. So let's say this is P1, the pressure P2 and P3. P1 has the biggest pressure because it's already perpendicular to the surface. As the angle here is smaller than this one, so P2 is bigger than P3. We have many uses of pressure in our daily life. For example, the school bags having white straps so that the pressure exerted on the shoulder is less. As A gets bigger, the pressure gets smaller. We cut things with a sharp knife because the tips of knives have less surface area, and as the force of our hand falls on a very small area of the object, it produces a large pressure. The minimum area, the most pressure, so the more sharp the knife is. Why it is difficult to walk pencil heels and easy to walk with broader shoes on soft hand. You see how it is hard for Lady Gaga to walk on sand. Here in the high pencil heels, the area is small, so pressure is more. But in a broader shoes, the area is large, so pressure is less, so easy to walk on sand. Camels move faster in sand because it has flat, broad feet, which increase the area of contact. Hence, pressure is reduced and make it easy to walk.